going to record, and then I'm going to share a screen in a minute. Oh, hello, Oski. Great background, Will.
Yeah, I'm very sorry. I need to change it back.
No, why are you sorry? This is fantastic background for today. Okay, let me get started. So today is supposed to be lecture 15, but we are finishing up a little bit of lecture 14 that we have left. And what we're going to do is discuss some ways of finding chance. Let me remind you where you are. So we did simulation last time, and we ended up by simulating a game of chance with the Monty Hall game. And we noticed something interesting about chances. So today we are going to talk about chances, and then Professor David is going to pick up and talk about methods of sampling and distributions of large random samples. And so we're going to talk about finding chances, but I want to remind you not of the details, but of the observation that we had in the Monty Hall example, which is that the car that this contestant hoped to win, in the end, is either behind their door, the door that they originally picked, or behind the other door that's left. Right? So it's either here or there. It's either in place one or place two. There's no other way. But those two places are not equally likely. Just because there are two options does not mean that they are equally likely. And that is an important thing for us to keep in mind. So just so that we, for some reason, I have given myself a screen where I cannot see my own slides. Okay. So we're going to give ourselves some basic rules of chance. And one of the things that I hope you will notice is that the rules that we are going to write down or discuss are really rules of proportions. Sergio, the demo, if you open the lecture 14 demo from last time, that will do. And then Professor David has another demo. Okay, so the rules of probability that we're going to write down are just rules of proportions, essential rules of proportions. But what we're going to do is organize the way we approach situations which in formal language are called experiments that involve a succession of random events. Right? So you have a random, what is called a trial. It's like a game that you play, and that you have a succession of these. We are going to organize our approach to how we deal with these so that when you find a probability, you have some degree of security that you have, yes, got the right answer. And even if you have studied some probability before, and certainly if you have not studied probability before, I hope that you will find this structured way of approaching a situation helpful. So keep in mind that today we are not going to focus on is the answer to this question 1/5 or 3/5. Rather, we are going to focus on what was the method by which we arrived at the answer and how can you apply that method in other situations. Okay, so the basic rules of probability are, as we said, the rules of proportion. So the lowest value is 0. This is the chance of an event that physically cannot happen. It is impossible. The highest value is 1, which we will also call 100% interchangeably. And that is the probability of an event that is certain to happen. It has to happen no matter what. Okay, we are going to use the term complement for what happens if your event does not occur. Okay, and a natural rule of proportion is that if your event has chance 70%, then the chance that it doesn't happen is 30%, what's left over. Now we will be looking at what's left over as a method of problem solving. So keep in mind that we are almost never going to give you you are almost never going to be in a situation of the entire calculation being this event has chance 60%, what's the chance that it doesn't happen? It's not going to be that way. we are going to have to recognize that the event that it doesn't happen is actually useful in the situation. Okay, so keep in mind this rule, but then we'll figure out how you decide when you use it. Okay, we are going to use percents and decimals interchangeably. Use whatever is convenient for you. I'm going to use the words probability and chance interchangeably. Use whichever one you prefer. Okay, so the simplest probability calculations are those where you have an assumption of equally likely outcomes. And I want to insist that that you keep in mind that this is only an assumption. If I give you a die and I ask you what's the chance that we're going to roll it, what's the chance that you see the face with 4 spots? A natural answer is 1/6. But that answer assumes that the die is not loaded. All right, so there is an assumption that this die that you have never seen is fair. And under that assumption, probabilities are just proportions. Okay, so an event is just something that happens. When you roll a die, an event could be that the die shows you 6 spots. All right, then the natural set of outcomes of rolls of a die is 1, 2, 3, 4, 5, 6. How many of those events, how many of those outcomes are 6 spots? 1. If you assume that all the outcomes are equally likely, that all the faces are equally likely to occur, and that is your assumption, then the chance of getting a 6 is 1 outcome that makes that event happen divided by the total number of outcomes, that is 6. So let's use this to try to answer a question. I have 3 cards, and I have given the cards names, but just think of them as a red card, a blue card, and a green card. And now we are going to introduce some language. So I shuffle them, which means I mix them up so that all arrangements are equally likely. And I'm going to draw 2 cards at random. That means shuffle once, draw 1 card. Without replacement, do not put it back. Shuffle the remaining 2, draw the 2nd card. Questions about the experiment? Samit, these are slides from lecture 14. Experiment clear? Okay. And then the question that I'm asking you is, what is the chance that I get the queen followed by the king? And I believe this the slide says there's a demo, but this is where I'm going to live dangerously and try to see if I can share my iPad screen. Working? Great. So what I'd like to do, I find Jupyter notebooks a little restrictive when we're doing probability calculations. You've got to be able to sort of sketch things. And so we are going to draw. We're going to visualize, okay? So we have a red ticket, a blue ticket, and a green ticket, or maybe they were called cards somewhere. And yes, notability. There's some product placement for you. So this picture is a good one to have in mind. And today, as it's the first time, I will write at random. That means every card is equally likely to be drawn each time. But after this, we'll just write 2 draws, and we have to specify what we are doing after the first draw. So our problem, I think, said that the 2 draws were going to be without replacement. Okay, and so what's equally likely in this setting? I think a natural assumption, and then can be even a definition, is that each pair is equally likely. So you have 6 pairs. And that's the assumption. And so capital P is this common notation for probability, but today I will actually just write things in words. Chance of getting, what was it? Somebody remind me of the event? What followed by what? Color. So green followed by blue. Agreed? That's what we're trying to find. Okay, so where's green followed by blue? Green followed by blue is right here. And so assuming equally likely outcomes, one out of 6. Okay, now it's not that final answer that is critical, though it is useful to be able to get that answer. You can see that I have 3 tickets and 2 draws so that I can actually list the 6 ways. However, if you have more cards and more draws, you need a better mechanism than this. So we are going to observe something about this 1/6, which is that you can imagine this experiment being done in sort of chronological order, right? First, you draw one, and then from the rest, you draw the other. And a great way to imagine proportions instead of probabilities is to imagine the entire data 8 class, 1,440 people, with this box. All right, so you have each one of you has a box that has a red, a green, and blue ticket. And each one of you is going to draw at random without replacement. And the people who win are the people who get a green followed by a blue. That's the rule of the game. Okay, so everybody shuffles and everybody draws 1 card. Already some fraction of the class has lost. What fraction has lost? At the first draw. It's the people, the winning people have to get a green the first time, so everybody else has lost. Right? The people who got a blue the first time or a red the first time are out of the game. So what % of people are still in the game? These are the people who could possibly win. What % of the people are still in the game exactly? 1/3 of the people are still in the game. Okay. But look at their tickets in their box. How many tickets in everybody's box at this point? 2, and it's the same 2. All of these people drew the green the first time, so all of these people not only have 2 tickets, they have the red ticket and the blue ticket. Okay, so we're not done. We have said that these people now get to draw again, and they need to get what? They need to get the blue one. So out of their 2 tickets, what's the chance that they get the blue one? 1/2. So of your original 1/3 people, 1/2 will win this game. Right? Now that's not quite in chronological order. When we write 1/2 of 1/3 is the second one first. So we instead write in chronological order. 1/3, that's the fraction that remain at the first row. And then you know that that's times 1/2. And we have to talk a little bit about what that second fraction means. Okay, but first you will see that this way of calculation also gave you the 1/6. You agree, everybody? All right, terrific. So let us write down what these terms mean. The 1/3 is very easy. 1/3 is the chance that the first card is green. Okay. What is the half? It is actually not the chance that the second card is blue, because the box changed, right? So it is the second chance that the second card is blue, given that your box contained a blue and a red. This is called a conditional chance. That the second card is red, given that the first, sorry, not red. Second card is blue, given that the first was green. And here you have a particular instance of what is called the multiplication rule. I'll write down the rule and look at consequences. So this is the chance that two events both occur. And what are the two events in this case? The two events are first green, that's the first event, and the other one is second blue. The chance that two events both occur is a product of two chances, that is the chance that the first one occurs times the conditional chance that the second one occurs. Given that the first one happened. Now, that's a long mouthful, but what it's really saying is this. You find the proportion of times you get the first event. Now, among those outcomes, what proportion of times do you get the second event? Your answer is a fraction of a fraction. It's a multiplication. And this is something to note. When you multiply two fractions, is the answer that you get bigger than each one or smaller? It's smaller. So what you're noticing is that if you put more and more conditions, I want this and this and this, I want cake and ice cream and balloons and a Tesla wrapped up in a red bow, the more you want, the less likely you are to be satisfied. Your probability is going to be a fraction of a fraction of a fraction of a fraction. It's not only probability theory, there's a life lesson in there. All good? Questions? Okay, so we now know how to handle two events both occurring. Here's your multiplication rule. And a summary of the discussion that we just had. Okay, and so now I'm going to ask you another question, which is same experiment. I'm going to draw twice at random from red, blue, green. What is the chance that one of them is blue and the other one is green? That's the question that I'm going to ask. And now at this point, please don't start thinking about what the answer is. Let's think about method. Okay. Whenever you have a situation where you need to find the probability of an event, you should think one trial at a time. In our previous question, it was very specific. We wanted first the green and then the blue. So we asked ourselves, what does the first one have to be? The answer was green. Immediately we could write down 1/3, and we knew the second one, they would have a times something, times something, times something. Let's play the same game here. Okay, I want the chance that one of the cards is a king and the other one is a queen. So one of them is blue and the other one is green. So in this situation, if I ask you, what does the first draw have to be? What can you tell me? Anything? Yes, exactly. So one of the things, by the way, let me answer some things on the chat. The question that I asked is, what does the first draw have to be? The answer to that cannot be a fraction, right? It has to be color, set of colors, something, right? And a lot of people are saying, I actually don't know what the first card has to be. It could be blue, it could be green. And the minute you can't write down, and depending on what that is, the second card has to be this or that. The minute this gets complicated, there is a signal to you. This event can happen in multiple different ways. Let's just start listing the ways. Okay, that is a very key method to be using. When the event happens, when you can't quickly write down what has to happen the first time, start listing the ways. Okay, so I still have this. And I want, now I'm going to start using notation. One green, what is wrong with me today? Okay, one green and one blue. Okay, so I don't know what the first draw has to be. So I'm just going to start writing the different ways. And this works, and also this works. Agreed? Okay, so now look, you want a green and a blue. You are very tolerant about which order they come in. You're easy to please. When you are easy to please, the chance that you are pleased is higher. So what you have done is you have partitioned this event into two ways it can happen. And these are two distinct ways. And so your chance is 2 out of those 6 overall outcomes. Right, so your chance was 2 out of 6. And that is the 1/6 plus 1/6. So the answer itself is not the main point. The point is the sequence that you took. You said, well, I can't say what the first one is, therefore I'm going to list the ways. And I'm just going to find the chance of each way and add them up. Pooja, I will simply, you don't have to take pictures of anything. I will simply post this PDF. Sound good? Well, the multiplication rule is for when 2 events have to both occur. So we are using the multiplication rule 2 times. This 1/6 is an application of the multiplication rule. This 1/6 is also an application of the multiplication rule. We are now saying both of those satisfy us, and therefore we are adding. Okay, all right. So the last thing that we're going to do is look at a situation where this is not so easy either. So here we have an addition rule summary. If an event happens in exactly one of 2 ways, then you write down the your chances, the chance of the first way plus the chance of the second way. And obviously you could have a third, fourth, and fifth way as well. Okay, and your answer is greater than or equal to the chance of each individual one. Okay, so your question here says the chance of at least one head. I am going to go to my, so in fact, you can certainly do 2/3 times 1/2, but you have to justify that, right? You can say the first card can be either blue or green, and then given that the other card has to be the other color, you can use this because your all the colors appear in the same proportions in your box. If your colors appeared in different proportions, that would not work. Okay, I'm going to ask you a question that is slightly different from the one on the slides. We're going to roll 4 dice. And by the way, if I say, actually, okay, this word, die, is this object. I'm not good at drawing, sorry. Right? That is a singular. Dice is multiple of these. That's the plural. So you cannot have one dice. You have one die. Don't blame me. I didn't make up English. Okay. So what we're going to do is we're going to roll 4 dice. And I want the chance that I get at least one occurrence of this. Okay. And I am going to follow my process that I laid out. Okay, so I'm going to follow my process was I'm going to ask myself, what does the first roll have to be? Well, you know, I can't answer that cleanly, right? The first roll could be a 6, it could not be a 6. Depending on what it is, the next roll, what does the second roll have to be? Well, I don't know. It could be a 6, it could not be a 6, depending on the other ones. And what is this a signal for me to do? This is a signal for me to start listing all of the ways. Good. So give me one way this could happen. How about non-6? I'm just going to list non-6, 6, non-6, 6. Does that work? Somebody else write a few more. It's not the only way. Yes, this works. This works. How long do you want to continue? Etc. This is tiring. Agreed? And it is because something is tiring. You could, in principle, write them all out, find all the chances and add up. That's fine. But when it is tiring, we try to find faster ways. And what I notice is at least one, in this case, is 1 or 2 or 3 or 4. What's the complement? In words. If you don't get at least 1 6, what do you get? No 6s. Which is just no 6s. It's a shorter list. What is the list for no 6s? Well, the list is n, 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 just one entry. Can we find the chance of that? Yes, no, maybe. What do? We ask ourselves, what does the first roll have to be? It has to be a non-6, 5, 6. Immediately, we know. The minute we can write down, what does the first roll have to be? We have 5, 6 times 5, 6 times 5, 6 times 5, 6, and we're done. Ah. So the chance that this does not happen is 5, 6 to the 4. So chance of at least 1 6. And the beautiful thing about this calculation, probably we're just looking at the chances that there are no sixes. In that case, it really doesn't matter. It's just all of them have to be no sixes, have to be not six. Okay, the wonderful thing about this calculation is what if there were, oh, I don't know, 17 rows? What's the chance of at least 1 6? Yep, you just replace the 4 by a 17. It's not a more complicated calculation. The logic is the same. Okay, so what I've done after taking up a whole lot of Professor Wagner's time is I hope I have given you a method of approaching problems. We have 1 minus, again, we have 1 minus, Patrick, because this here is the chance of no sixes. Right, and what we want is the chance of at least 1 6. So we want the complement. Good. Okay, so what I would like to summarize this with is try to focus on method of problem solving. And then you will be able to solve a variety of different problems that look different from each other. Do not think about what is the formula, and don't try to say, well, they did this problem like this, the words kind of sound the same, and therefore I'll do this one. Don't do that, that doesn't work. For all those of you who are watching the video, I'm going to post this on Ed and are not actually in lecture. This is a really bad lecture to fast forward through the talking, right? Listen to the talking, if anything, fast forward through the calculation. All right, I'm done.
All right, thank you. That was great. Perfect. So we're gonna continue diving into probability and randomness. You may have noticed that we're a little bit behind the schedule on the website, and that's no problem. We'll get there. So why are we spending so much time on probability, random sampling, randomness? Let me just give you a zoomed out view before we dive back into the technical details. Randomness can be our friend, because when we're doing an experiment and we want to make sure that we have no systematic patterns, biases, confounders, one really powerful way to do that is to choose randomly who's involved in our experiment. And then when we want to analyze the effects of making a random choice, then it's helpful to have a really deep understanding of randomness and how to calculate what's the probability that different things happen if we do it randomly. All right, so these rules of calculation are going to help us understand the effects of choosing randomly. Give me a moment here. And I'm going to get set up. So I want to start talking about choosing random samples and their properties. And I'm going to do that in just a moment. But some reminders, homework 5 is due tomorrow or tonight for 5 extra bonus points. So don't forget. Project 1 is due this Friday. Don't forget tomorrow for 5 extra bonus points. And don't forget our midterm is coming up on October 15th. All right, let's check and see how we're doing on probability. For those of you asking for the slides, these should be on the website. I want to do a problem together. and see how we're doing. This is our checkup on probability. So let's assume we have a population of 100 people, and 2 of them are Rick is one of them and Morty is another. And I want you to imagine that we sampled 2 people from this population without replacement. Okay, so without replacement means I randomly pick one of the 100 people, all of them equally likely. And then whoever that is steps aside, and there's now only 99 people, and I randomly pick from those 99, all equally likely, and that's my second person, they step aside, okay? So we'll never pick the same person twice. That's what without replacement means. And now I want you to do some probability calculations for me. So take a moment to think about, before you write in the chat, think about how to compute the probability that this sample contains both Rick and Morty. Both Rick and Morty are in the sample. All right, let's start by thinking about the method. Professor Adhikari suggested we think about the method. So we have a couple of methods here. One method that we know would be to list all the possible outcomes. Another method we know would be to ask what has to happen first and then what has to happen second. And another possibility would be to try to figure out if we could use like the addition rule. So which of these rules do you think is appropriate? Should we do addition rule, multiplication rule, list all the possibilities? Okay, I see a lot of answers. Some saying multiplication rule, some saying addition rule, some saying both. Why don't you tell me, one person type in the chat, a reason why you think a multiplication rule might be useful here? Because the and 2 events must both occur. Yeah, we want Rick to be in the sample and we want Morty to be in the sample. Another way to look at it is what has the first person? Okay, what? Yeah, that sounds like it's hinting at a multiplication rule. What's the reason why you suggested the addition rule? Anyone want to give a reason why someone might think the addition rule is relevant here? Good. It's because they could occur in either order. It could be that we picked Rick first and then Morty, or we picked Morty first and then Rick. Great. So let's compute the probability that we pick first Rick and then Morty. Well, that we can compute using the multiplication rule. Because the probability that Rick appears first is 1 out of 100. There were 100 people, and one of those, we have 1 out of 100 chance that we pick Rick. And then the probability, assuming that happens, that we pick Morty second is there's 99 people, and so it's a 1 out of 99 chance we choose Morty from the remaining people. And we can use the multiplication rule to multiply those 2. So this gives me the probability that first we picked Rick and then we picked Morty. But that's not the only way that we could be satisfied. There's 2 ways we could be pleased. The other way we could be pleased is if we pick Morty first and then Rick. What's the probability that we pick Morty first? That's 1 out of 100 because 100 people to pick and Morty is one of them. And then if you pick Morty first and Morty is standing on the side and there's 99 people left, what's the probability that you pick Rick out of those 99? That's 1 out of 99 because There's 99 people, all equally likely to be picked. Rick is one of them. Okay, so we have now used the addition rule and the multiplication rule to compute the answer, and the answer is about 0.0002. Now, there's another way we could have gotten the answer. Remember, one other method you could use is list all possibilities. So suppose we write down the possibilities by listing who we picked first and then who we picked second. Well, what are all the possibilities? One possibility is we pick Rick and then we pick Morty. That's one possible outcome where we're pleased. Anyone want to give me another possibility, another possible outcome where we're pleased? Morty, Rick. Anyone want to give me a third possibility where we're pleased? Trick question, there is none. Those are the only two ways we're pleased. Okay, so if we list all possibilities, there's two of them where we're pleased. How many possibilities are there in total? Well, we could start trying to write them down, but we get really tired. What we would find very quickly, if we spotted the pattern, is that there's 100 possibilities for who we pick first and 99 possibilities for who we pick second. So in total, there's 9,900 possible outcomes. Two of those, we are pleased. I just listed the two we're pleased. So we can divide because they're all equally likely, and we get the same answer. Okay, so there's two different ways to solve that problem. All right, let's do part B. Part B, now I want you to compute the probability that neither Rick nor Morty is in the sample. So just think about this for a moment. Think about what method you might use. Yeah, good. 1 minus. Compliment. My compliments to Professor Adhikari for teaching such a great lecture. She really killed it, especially with those die. Okay, so good. You can see that either both Rick and Morty are in the sample or they're not. So the answers to part A and part B have to add up to 100%. They have to add up to a probability of 1. So whatever we got in part A, 1 minus that should be what we get in part B. So once we've solved part A, wait a minute. What's wrong with what I just said? That was baloney. Yeah, you got to call me on my baloney. That was total baloney. Because what if Rick is in the sample, but not Morty? Okay, so these were not compliments, actually.
Hey, Professor David.
Yeah.
Can I say something after decades of having done probability?
Yeah.
This happens all the time. It's part of the process, right? So when this happens, it's like getting an error message when you write code, right? The only thing is you have found your own error. And when this happens, go back to basics, ask yourself, what does the first trial have to be?
Awesome. Thank you for the encouragement. All right, everyone. What does the first trial have to be if neither Rick nor Morty is in the sample? Well, this answer to the what should be a person, like a name. Shouldn't be a number, because the first thing we do is we pick one person. Has to be anyone but Rick or Morty. Can't be Rick, can't be Morty. Okay, that's good. What does the second person have to be? Again, anyone other than Rick or Morty. So that's good. We can answer both of those questions. So which rule does this suggest we should use? Multiplication rule. Yes. Excellent. Oh, we're doing so good here. So happy with you, how you're doing. This is looking good. All right. So if the first person has to be someone other than Rick or Morty, what's the probability that happens? The first person we pick is someone other than Rick or Morty. 98 over 100. There's 100 people. They're all equally likely, and 98 of them we'd be pleased with. Okay, now let's assume we were pleased with the first person we picked and they're standing aside. There's someone other than Rick or Morty. What's the probability we're pleased with the second person we pick? In other words, what's the probability the second person we pick is someone other than Rick or Morty? Yeah, 97 out of 99, because there's 99 people remaining. And Rick and Morty, we didn't pick yet, so they're still in the 99. So there must be 97 others who are still left. All right. And so using the multiplication rule, we multiply and we see that there's a 0.96 probability that neither Rick nor Morty are in the sample. Okay, good. I'm pleased. You're doing well with probability. So let's move on to sampling. I'll take a pause for questions here. What will be the complement to part A of the question? Good. The complement to part A is that it's not true that both Rick and Marty are in the sample. So that might happen if Rick is in the sample but not Morty. It might happen if Morty is in the sample but not Rick, or it might happen if neither of them is in the sample. We did 97 in the second part. That's right, because we picked one of the 100 people and had them stand aside. That wasn't Rick or Morty. So there were originally 100 people, including Rick and Morty. One of them who wasn't Rick or Morty stepped aside. So we're left with 99 people, including Rick and Morty. So that's Rick and Morty and 97 others. So if we want to pick someone out of those 99 that's not Rick or Morty, then we got to pick one of those 97 remaining people. Can I explain why we can't use the complement? You can use the complement if the event down here, the second event, happens whenever the first event doesn't happen. But there's a problem. You could have the first event could happen, you could have the second event could happen, or you could have something else happen. There's a third possibility that's not accounted for here. So these two probabilities don't sum to 100% because there's a third possibility that could also happen. Those three probabilities have to sum to 100% if I calculate all three of them, but I haven't calculated all three of them. All right, so let me give you a preview of what we're going to learn on Friday. Sorry, we're so far behind. We're going to learn about choosing a random sample. If you have a population of people, we're going to learn about different ways that you can pick a sample, pick some of them. And there's multiple different kinds of random samples. We will show you deterministic samples and random samples. And a deterministic sample is one where there's no chance involved. Like that might be I pick every third person in line. And a random sample is where there's chance involved and where I can compute the probability of every possible outcome of the sampling. In other words, every possible combination of people in the sample. And so we're going to work through different kinds of sampling and measure their effect on experiments if we use random samples on Friday. So I'll see you on Friday, and thanks so much for your patience with us. Don't forget to turn in your homework and work hard on your project.
Guys, I just want to say something, which is that we actually have some space built into our schedule in the next couple of weeks. So what we'll do is we'll just reorganize the calendar so that you know what's coming. We're fine. It's not as alarming as you might think that we're a little bit behind. I am now going to stop the recording.